Consumer and producer surplus. So, assuming that the market settles at an equilibrium point, then when we look at our supply and demand for a particular good, then the equilibrium point is where the market will settle, with the price being P star and the quantity being Q star. So you can see this notated on the graph below. This is where supply and demand intersect. This is what economics tells us will happen in a free market, that the price and quantity will settle to this amount because that is where the market says that we will land. Because we end up at this point, some interesting things happen for both the manufacturer and the buyer. And those things are called consumer and producer surplus. So we're going to investigate these and see what that means in terms of both the definite integral and in terms of economics. Both the consumer and producer make money from the market being in equilibrium. We'd like to determine exactly how much money each category is making by having the market settle at P star Q star. So remember, the demand equation, which you see here, is a decreasing function because as the price is high, the quantity that the buyer will buy is low. And as the price comes down, the amount that they're willing to buy goes up. So if we settle at the equilibrium point, that means that there are people who would have been willing to pay more for this item. So as a whole, the consumer gets to save some money because they would have been willing to pay more than the equilibrium price. We can see this shaded in with this yellow triangle here. That area is going to represent the amount of money that consumers have saved from buying at the equilibrium price rather than the price that they would have been willing to pay. This is called the consumer surplus because as a whole, this is how much consumers have saved. Now, mathematically, we have to think about what we know about area between curves. Back in Calculus 1, the way we computed this was to take the area under the top curve minus the area under the bottom curve. So here, if you look at the representation in the yellow shaded part, we can see that the top curve is the demand curve. So if we were to set up an integral to represent our consumer surplus, we would have our demand equation, which we'll call d of q, as our top curve, minus, now the bottom bound of this and the bottom curve we're going to use is this equilibrium price. So if you have a horizontal straight line, then that means y equals just that line. Here we're using p's and q's. So here we have the p star constant as our lower bound. Now our variable here is q, so we have dq. I want to point out that our independent variable here is q, that's where the x usually goes, and our dependent variable is p. So when we talk about p star as a function, that is a y value, like 5 or 10. If you were to graph y equals 10 on an xy axis, it would just be a horizontal line. It's the same idea here, even though we're using q's and p's. So we have our top curve minus our bottom curve. But we also need to think about what are the bounds of integration. So for supply and demand, quantity always starts at 0 because you can't have less than 0 of a good. We're going to keep integrating until we get to our intersection point. At that time, the independent value is q star. So we're going to integrate from 0 to the equilibrium quantity of the demand curve minus the equilibrium price. That's the equation that will give us that yellow area. So if we have an equation for the demand curve and we have an equilibrium price, we can set up an integral to calculate the exact surplus that we have by settling at the equilibrium point. Let's see an example of what this would look like. Example 1. Consider the supply and demand model given below. Use the information given to determine first the equilibrium price and quantity, and then compute the consumer surplus. So remember, the equilibrium price and quantity is where supply and demand intersect. So you can see here the demand is our decreasing function, the supply is our increasing function, and our P star and Q star are labeled. So here, our equilibrium price is going to be $375 per unit. That's the price that we're going to settle on. And then our equilibrium quantity is 10,000 items. So when the price of an item is $375, 10,000 of them will be manufactured or supplied, and 10,000 of them will be demanded. So this is an efficient model at the equilibrium point. So now we want to compute the consumer surplus. So remember, this is the amount of money that the buyer saves because they would have been willing to pay more money. So maybe they were willing to pay $400 or $425, but they didn't. They got it for the price of $375. So all these high prices that are up above the equilibrium line are prices they would have been willing to pay. So the amount of money that they saved is the area between the equilibrium price and the demand function. So to calculate that area, we have two different methods. The first method is a nice geometric model because notice here that our functions are linear, which means that they're lines. That allows us to look at this and see that our shape or the area we're interested in is a triangle. And if you have a triangle, you can certainly calculate area using the standard formula 1/2 base times height. So 1/2, my base here, my quantity goes from 0 to 10,000. So my base is 10,000. And my height, I'm going from 375 to 500. So the difference between those two numbers is going to be my height. So that's going to be 125. So if I multiply these numbers together, I get that the consumers have saved $625,000 by settling on this equilibrium price. Now, we also want to be able to use our techniques of integration to talk about this area. We should, hopefully, get the same exact outcome of $625,000. But let's see how we do this in case in a future example we don't have all the same information. So in order to figure this out using integrals, we need an actual function for our demand. So based on the information given, we can certainly generate a function. How do we do that? Well, we recognize that our function is linear, and we notice that we have 2 points on our line. So here, this 40,000 is the amount we have when p equals 0. So remember, your p is your y value. So we have 40,000, comma 0. And this point up here is going to be the point where our q is 0 and our p is 500. So we have 0, comma 500. So we have 2 points on our line. We actually have 3 because we also have the point q equals 10,000, p equals 375. But we'll use the intercepts instead because the zeros make the calculations a little bit easier. So remember, the equation of a line is typically given as y equals mx plus b. However, we don't have x's and y's in this example. We have p's and q's. So instead of an x, we're going to replace that with q because quantity here is our independent variable. And instead of y, we're going to have p. So we have p equals mq plus b. So that's also the equation of a line, only now we're using the same variables that we have in our model. So we need to calculate the slope of this line. We can see that it's downward sloping, so we're expecting the slope to be negative. So if you think back to algebra, slope is computed by doing the change in y over the change in x. So my change in y here is 0 minus 500 divided by 40,000 minus 0. I can simplify this and I will get negative 1 over 80. So my slope here is negative 1/80th. So thinking about my demand equation, I know that I'm going to have P equals negative 1/80th Q, but I still need my B. So remember, your B represents your vertical intercept. So when Q is 0, we know that our intercept is 500. So I will have plus 500. So by finding the equation of the line, I have the equation of the function. So now I can set up integrals to calculate that area. So we said that mathematically what we're going to do is we're going to take the integral from 0 up to Q star. So we're integrating from 0 to 10,000. That's where we stop because that's when we hit our equilibrium point. And in Calculus 1, we learned that area between two curves is top curve minus bottom curve. Well, we just computed the function for our top curve. So negative 1/80th Q plus 500 minus, now my bottom curve is this horizontal line. So when I have a horizontal line, it's represented by the number that it equals. So this line is P equals 375. So that's the equation of that function, which is the horizontal line. This is dq, because again, my variable is q. So I can either compute this using some sort of calculator or computing software, or I could do it by hand. But when I plug it all in, I'm going to get that this is 625,000. And again, that's in dollars. So that matches what I got when I did this geometrically. So notice here that sometimes you're going to have to generate the function. Other times you'll be given the function. But you have to be able to look at the model, figure out the area you're looking to find, and then use tools that you have to calculate it. We don't need to do this both ways, but it's nice to know the various ways we can solve this, so depending on the situation, we have different tools to approach it. So we know that the consumer has saved $625,000 by moving to the equilibrium price and quantity. We haven't talked yet about what the benefit will be to the producer. So that'll be our next definition. So again, both the producer and the consumer are going to benefit from going to the equilibrium point. We just talked about how the consumer benefits, but now let's talk about how the producer benefits. So remember that when we talk about the producer, we're talking about the manufacturer that supplies our good. By moving to the equilibrium point, we now are able to charge a higher price than we might have been willing to do earlier. So what that means is we may have been willing to supply some of our good for a lower price. But by moving to the equilibrium, we're able to charge a higher price, which is beneficial for the manufacturer because that means they make more money. So by moving to this higher price, we can see just how much they benefit. If you look at the picture here, this is shaded in green. This is the extra amount of money we're going to get by charging the higher price that comes at equilibrium than we would have previously charged. So how do we represent this mathematically? So again, we want to find the area between two curves. And notice that we're integrating from 0 to Q star. So here we have 0 to whatever the equilibrium quantity is. And again, to find the area between two curves, we're going to do top curve minus bottom curve. So here my top curve is my equilibrium price, P star, minus my bottom curve is whatever my supply function is, which is a function of Q, dQ. So to find the area between the curves, I'm now doing P star minus my supply function. That will give me the area, which represents the amount of money that the supplier has saved by moving to the equilibrium point. So let's look at the same example we were just looking at for the consumer and see how much the supplier saved in that scenario. So in our model, remember that our equilibrium point is P star equals 375, Q star equals 10,000. Now we're interested in the producer surplus, which means that we're looking for the amount of money that the producer saved, which is the area between the equilibrium price and the supply function. So if we shade that in, it's going to be represented by this area here. So again, we're a little bit lucky in this case because this area is a triangle. And when that happens, if your function is linear, you can certainly approximate the area using 1/2 base times height. So if we do that here, we have 1/2. Again, my base is going to be 10,000 units. And my height is 375 units. When I multiply those together, I'm going to get $1,875,000. Are you surprised? This is a little deceiving because if you look at the pictures, it looks like the triangle on top is bigger. But when you actually mathematically calculate the surplus, the bigger surplus happens for the supplier. That just tells me that my model is not to scale. The numbers, well, the math doesn't lie, but sometimes perspective of how big things are, they can. So you have to make sure you look carefully at what you're computing and you compute carefully. Because if you just eyeballed it, it'd be easy to guess that the consumer surplus would have been bigger because the triangle certainly looks at least equal to, if not bigger. But here, when we compute it mathematically, we find out that the producer surplus happens to be bigger. So again, if we want to set up integrals to find this area, we would need an equation for supply. So again, we want to find if we have 2 points and we want to find the equation of the line. So notice here that my supply goes right to 0, 0. And then I also have the equilibrium point of 10,000, 375. So I can use these 2 points to generate the equation of my line. So remember, instead of y equals mx plus b, we're going to have p equals mq plus b. So my slope will be change in y over change in x. So my change in y is 375 minus 0 divided by 10,000 minus 0. If I do some algebraic simplification, I'm going to get 3 over 80. If you're uncomfortable simplifying, you can certainly use a calculator to assist you by looking for common numbers that you can factor out and cancel to simplify your fraction. So going back to my equation here, I'm going to have P equals 3 over 80Q, and then I need my B. Remember, my B intercept is where my line crosses the vertical axis. I notice here that it happens at 0, 0. Therefore, my B is 0. So I don't need to write that. I can just leave it as 3 over 80Q. So now I have my supply function. So when I set up my integral, I'm going to integrate from 0 to the equilibrium quantity, which is 10,000. And now I need to be careful about how I set this up because again, I need to do top curve minus bottom curve. My top curve here is the 375 when I'm computing the producer surplus. Minus, now I'm going to subtract off my function, which is 3 over 80Q dQ. Now in this case, I only have one term, the 3 over 80Q, because my B was 0. If I had a B that was not 0, I would really want to use parentheses around my supply function because the minus has to be attributed to all the terms in the function. So again, when I calculate this, I can do it by hand or I can do it with my calculator. I'm going to get 1,875,000 as saved money from the producer side. So in this scenario, the producer certainly got the better deal because the consumer only saved $625,000 overall, but the producer saved almost $2 million. Example 2. Suppose that the demand for a product is given by P equals 35 minus Q squared. Additionally, supply is given by P equals 3 plus Q squared. Determine the consumer and producer surplus for this item. So I've provided the graphs of these functions below. Now, notice here that the colors have changed. What's important is to remember that supply is going to be an increasing function and demand will be a decreasing function. So in order to compute the consumer and producer surplus, the first thing we're going to need to do is figure out the exact point where they intersect. We need that equilibrium point for our calculations. So because these are quadratic functions, both of them, we can solve for this point by setting these two functions equal to each other and solving for q. So over here, I have 3 plus q squared equals 35 minus q squared. You can also graph both of these on a calculator and compute the intersection point. So here we want to combine like terms. So I'm going to bring this q squared over to the left and the 3 over to the right. So when I bring the q squared over to the left, I have to add it. So then I have 2q squared. And when I bring the 3 over to the right, I have to subtract it because it was positive. So that will equal 32. Solving for q, I divide both sides by 2, and I get 16. And now I can take the square root of both sides. So when I take the square root, I get q equals plus or minus the square root of 16, which equals plus or minus 4. But we know here that we're talking about quantity, and it doesn't make sense for quantity to be negative. So that means that my q has to be 4. So q, remember, is our independent variable. So we'll label this right on the q-axis. The other axis, remember, is our price. So to get the corresponding price, we need to plug this q equals 4 value back into either one of our equations. It doesn't matter which one. So I'm going to pick the second one. So I have 3 plus q squared. So that'll give me 3 plus 4 squared. 4 squared is 16 plus 3 is 19. So my price per item at equilibrium is going to be 19. So I'm just going to draw my best version of a straight line here, and then another one over here. So now I have the tools I need to compute the consumer and producer surplus. So I'm going to start by computing the consumer surplus. So remember, consumer surplus is calculated by taking the integral from 0 to our equilibrium quantity, which we found to be 4, of our demand curve minus our equilibrium price. So remember, the demand curve is always the one that's decreasing. So that's given in our problem. It says demand is given by 35 minus q squared. So that's my demand, 35 minus q squared, minus, now I have to subtract off my second function, which is this horizontal line that equals 19. So again, I can simplify this before I do my computation, or I can enter it just like this into a calculator. I could do it by hand. I'm going to use my calculator, and when I compute this, I get $42.67. So again, this tells me how much the buyer has saved because the market settled at the equilibrium point, and that is represented by the area between the demand function and the equilibrium price. The producer surplus, which is how much money the manufacturer saves, is computed by looking at the area between 0 and the equilibrium quantity between the supply graph and the equilibrium price. So remember, your supply is the increasing function. And so the producer surplus is going to be the area between the supply graph and the equilibrium price of 19. So we'll shade it in over here, all that. So when we compute this, we're going to do top curve minus bottom curve. Order is important. So my top curve is 19 minus, now my supply function is the 3 plus q squared. There's more than one term, so I need to use parentheses. dq. So again, I can either use a calculator, I can do it by hand, I could simplify first or not simplify first, but either way, however you compute it, you're going to get that the producers saved $42.67. So it turns out that in this particular scenario, for whatever this item is, the amount of money that is gained from going to equilibrium is the same for both the consumer and the manufacturer. So what that tells us is that our model is fairly accurate, because if you look at the areas, they look equal. And when we compute it, we find that they are indeed equal. So here, we're able to see and calculate exactly how much is saved by everyone involved. Suppose supply and demand are continuous functions and some of their values are given in the following tables. Use the tables to answer the following questions. A, which table is supply and which is demand? So remember, one of the qualities of a supply function is that it's an increasing function, and one of the qualities of a demand function is that it's a decreasing function based on the relationship between quantity and price. So our first table, we see that the values decrease as quantity increases. So as quantity goes up, 0, 100, 200, the price is going down. So we said that our decreasing function is our demand function. Notice on the second table that the relationship is that we have an increasing function. We have the values 10, 14, 18, 22, 26. So those values are going up as quantity goes up. And that again explains the relationship that the supplier is willing to produce more as the price goes up. So our second table here is our supply function. Part B. What is the best estimate for equilibrium price and quantity? So remember, the equilibrium price and quantity is the point where supply and demand intersect. That means that they share a point. So we're looking for a place where the quantity and price for demand is the same as the quantity and price for supply. So looking down the table, when you get to a quantity of 400, you'll notice that both supply and demand give a price of $26. So they share this point in common. Since that point is shared, that has to be where our functions intersect. So that means that our equilibrium quantity is 400 and our equilibrium price is 26. So that's our Q star and our P star. Part C. Estimate the consumer and producer surplus. So here's where we need to think about what we know about approximating area under the curve on a table. So when we did this in Calculus 1, we needed to look at left-hand approximations, right-hand approximations, and best estimates for area under the curve. But remember, when we look at the area under the curve for consumer and producer surplus, we always look from 0 until Q star, the point where they intersect. So that means when we do our calculations, we're going to be looking between 0 and 400, because after that, we don't consider what is happening. So we don't need to look at 500 or 600 on our table. But then we also need to figure out how to incorporate what we know about area under the curve with what we know about consumer and producer surplus. So we'll start with consumer surplus. And remember, consumer surplus is going to be the area between two curves. And those curves are the equilibrium price and the demand function. So to imagine how this formula is going to work, we need to remember what we're doing when we compute our estimates. We were fixing our interval. We're saying what's happening between 0 and 100. When we do a left-hand estimate, what we're doing is we're assuming that the price is constant at 63 over that interval in order to put in a rectangle. But we have to account for the fact that we need to subtract off the equilibrium price. So instead of 63 times 100, we have to do 63 minus 26 to account for the fact that we're subtracting off that equilibrium price at every single point. So for consumer surplus, we're going to do a left-hand estimate and we're going to do a right-hand estimate. For the left-hand estimate, that means for the first 100 of these things produced, we're going to assume the price on the left. So that's 63. However, we have to subtract from that our equilibrium price to account for the fact that we're not looking between the function and the x-axis. We're looking between the function and the equilibrium price. Now, the next 100, we're going to pick the price on the left, where we'll do 51 minus 26, plus from 200 to 300, we'll do 100 times 40 minus 26. And then finally, from 300 to 400, we'll do 32 minus 26. So obviously we have to be careful when we crunch this number, but we can use our calculator. And when we crunch all these numbers, we're going to get $8,200. Now, that's a left-hand approximation. We also need to do a right-hand approximation. So now for each 100 units, we're going to pick the price on the right. So we have 51 minus 26 plus 100 times 40 minus 26 plus 100 times 32 minus 26 plus 100 times 26 minus 26, which is 0. Again, we're going to carefully compute what that number crunches to be, which is 4,500. So remember, our best estimate is going to be to average our left hand and our right hand estimate together. So we'll take the 8,200 plus the 4,500, we'll add them together, divide by 2, and that'll give us 6,350. So our estimate here for consumer surplus, we'll put this up by demand, consumer surplus is approximately 6,350. So now we have to do something similar for our producer surplus. We have to do a left and a right hand estimate. We're going to be going from 0 to 400. But now we need to think about how this 26 impacts our producer surplus. So remember that when we set up a producer surplus, our equilibrium price is higher than the supply prices. And so when we do top curve minus bottom curve, we're going to be doing 26 minus the price that we're using to estimate for supply. So when we do a left-hand approximation, we're going to have 100 times 26 minus 10 plus 100 times 26 minus 14 plus 100 times 26 minus 18 plus 100 times 26 minus 22. Again, we're going to carefully crunch all those numbers, and we're going to get 4,000. We also have to do a right-hand estimate. So for our first 100 units, we're going to pick the price on the right. So we have 26 minus 14. Then for the next 100 units, we pick the price on the right. So 26 minus 18 plus 100 times 26 minus 22 plus 100 times 26 minus 26, which is 0. Again, we're going to crunch that number, and we're going to get 2,400 for a right-hand approximation. So again, our best estimate is going to be to average the 4,000 and the 2,400. So we add those two numbers and divide by 2, and we get a producer surplus estimate of approximately $3,200. So in this case, the buyers won out. The consumer surplus was higher than the producer surplus. We are using what we know about Riemann sums and approximations of areas under the curve using rectangles, which is how we approximate area from tables, in conjunction with what we know about consumer and producer surplus. So if approximating area from a table is not something that you remember, you should certainly review how we do this using Riemann sums and rectangles to approximate.